everyone. Hello. Hello. It's the button, I bet. Very good. Okay. Hello, everyone. Thank you for coming today. My name is Craig Gruber. I'm the president of the New York chapter. And before we get going with what promises to be a very informative session, just a few announcements. Some of you may remember a long time ago, before COVID, we had this concept of chapter membership. And the way that worked is you could pay for, well, right now we pay at the door, but you could buy a whole year's worth of admission to the meetings at a discount, and also get a discount to our gala in June. So when COVID started, all the meetings were remote, and so we stopped offering those, but we've started offering them again. So we're in the middle of the year. So this is the "Do we have a deal for you" section of the meeting. So what we've come up with is for $125, it's admission to the remaining meetings of this year, plus all the meetings of next year, plus a $20 discount to June's gala. Now, I know that sounds like you're all ready to rip out your cell phones and sign up right away. And we weren't able to throw in a set of Ginsu knives, if anyone remembers what those are, but you do, okay. But it also will get you a discount to next year's gala. So that's this year's meetings, next year's meetings, two $20 discounts to the galas. It's over $100 worth of discounts. And that's live on the website in the membership section. You can sign up just the way you sign up to a meeting. Right there, mid-year individual, it's called. So this offer is going to be from today until the end of our May meeting. And then after that, we'll go back to the regular construct for the memberships. So that
$100 for the next program.
Which is $100. This normal membership is $100 for a year's worth of meetings. So that is that. Then, let's see. Scholarships. One of the things the chapter does is offer scholarships through the national organization. There's a page on the website for scholarships. If you know people who are in our field and have an economic need, we would urge you to point them to that section of the website under scholarships. Let's see, I think it's under about scholarships, and there's a whole process there where to send the applications and what they are, and we like to, really be helpful with those. Chapter awards. At the gala each year, the chapter gives out awards like Energy Manager of the Year, Energy Project of the Year, Young Energy Professional Development of the Year, Corporate Energy Manager. If you have ideas for a project or for a person you think has been exceptional, we want to hear about it. We evaluate it. The process is rigorous, no doubt about it. But I think, recognizing these people and these projects is a worthy task. So we'll be sending out an email next week along with how to make those applications and make us aware of those projects and people. And if you don't get any of that information, you can always send it to info@newyorkaee.org. AEE East is in Boston, June 7th and 8th. If you haven't gone to any of these regional AEE meetings, they're usually pretty valuable in terms of technical sessions and commercial exhibits. And lastly, we'd like to acknowledge our corporate sponsors this year: Dual Fuel, DNV, Innovative Power, Leidos, Empower, Metergy, Utilivisor, Train, NYSERDA, C-Power, Fisher Energy, EIS, EMAX, Systems Inc., Aramark, and NYIT. With that, I'm going to turn it over to Fred Goldner, who's going to introduce our session. Actually, I'm going to turn it over to Pat, who's going to introduce our speakers and our technical session.
Thank you, Craig. Tonight we have three speakers. One will be speaking on the utility perspective of district heating. One will be speaking from a construction and general contractors point of view, and one will be speaking from the view of a Sloan Kettering hospital and how they've used district heating in their facilities. Our first speaker will be Caitlin Sakata, and Caitlin is the co-lead of Con Edison's utility-owned thermal energy network group, focused on building out the utility strategic vision and implementing multiple pilot projects throughout the service territory. She's worked at Con Edison for 7 years and had prior roles managing emerging technology pilots, energy efficiency programs. Most recently as the manager of reforming the energy vision REF demonstration project group. And Caitlin, she has an MBA from NYU Stern and a BA in environmental studies from Bucknell University. Caitlin?
Is that mine? Okay, do I hit this now? Oh, F.
Oh, no. That's right.
This one? Okay. Okay, good. Is it supposed to advance?
Yeah.
And that's it. So thank you so much. And okay. All right, great. Hi, everyone. And to those watching virtually, I'm Caitlin Sakata at Con Edison, and I'll be giving an overview of thermal energy networks from a Con Edison perspective. I will say that had I come about a month and a half later, we would have some actual projects to present to you. We'll go through our RFI. So we're going to talk through the process, and then not a pitch to come back, but there will be some public announcements, I think, coming between April and June. Stay tuned for that. So we'll just go through why I'm here today. The Utility Thermal Energy Networks and Jobs Act, which is, we don't know it as UTENJA because that's a pretty bad acronym, but that's what people are saying, and go through the updates and where we are as a utility. So just to start off, I think it's great to have a diagram of what we're talking about. And so here, a thermal energy network has pipes that are in the ground providing water to a variety of buildings for heating, cooling, domestic hot water. You'll see the pipes and the little arrows, which represent the water, and you'll have, this is ambient, and what we're defining as ambient is between 50 and 90 degrees. So this is not, hot boiling water or steam system like Con Edison has in Manhattan, but instead helps to provide heating or cooling, whatever the needs might be, that then supplements by the heat pumps in the individual customers' buildings or homes. The heat's provided by usually geothermal borehole. Oh, yeah. Oh, yeah. Only if you guess.
Just minimize it.
I'm just going to bring it up here. It's a river. I think it's the bottom is blocked, but there's nothing down there. And that is a heat sink or source. So if you have a location that's close to a river or a lake or a body of water, if you need that water, you could utilize that, but also as a heat sink if there's some imbalance or your loop is running too hot. So we have the boreholes, and that provides heating and cooling that are in the ground. You also have waste heat. So from sewers, there's a lot of technologies that are doing that right now, and also data centers or other places that provide excess heat that can be utilized for the UTEN system. And then the only other piece here that I think I didn't mention is the hydronic pumps. You'll see those little cylinders, and that just is throughout that the loop to make sure that the water is being pumped and the pressure is consistent. So why are we here and what is UTENJA? So in July, Governor Hochul signed the Thermal Energy Networks and Jobs Act. And subsequently, the Public Service Commission came out with an order that was issued for the 7 largest electric, gas, and combination utilities in New York State. So what that did is provided an avenue for the utilities to offer up different pilot technologies and test different learnings to see if this is going to be a part of the solution for decarbonization and electrification in New York State. So decarbonization, I think most of you are familiar here with the Climate Leadership and Community Protection Act, or CLCPA. And so that's one piece to help get us to the goals of 2030 and 2050, 40% reductions of greenhouse gas emissions. The second, and just as important, is the jobs component. So broadly, it's important to build up our energy network. I think all of you here know that we could use a lot more good people in the room to get to these really aggressive goals. And primarily focusing on all the utility workers who are focused right now on the gas side of the house. And as we transition and move away from fossil fuels, making sure that those folks have another outlet or potentially possibilities for reskilling for jobs, potentially at a U10 type system in the future. The PSC also directed that we have 1 or up to 5 different pilots, at least 1 located in a disadvantaged community. That's essential because we have to make sure of equity and inclusion in any type of clean energy solution in New York State, and I think kind of broadly in the country as we move forward. And then the Public Service Commission also has to authorize and provide some recommendations within 2 years of what that's going to look like. And that's a big undertaking too. So the timeline started ticking kind of immediately, and we want to make sure that we have good projects and a variety of projects to have some varied learnings and make sure that we can move forward and have these projects be successful. Very quickly, I was talking, who was I talking to? I think about the kind of, I was going to go right into, okay, so we have this filing, which is very utility speak, and here's the ways that we complied, and here's where we're going forward. And I think he said, take a step back, and why are you even doing this in the first place? Is it just because you were mandated to do so? And obviously the answer is no. So I just wanted to provide a brief overview of the fact that there is some benefits. Geothermal has been happening in the state already, and the utility ownership of a potential network is not going to replace that market at all. We need all of those people. We need more of them, in fact, of contractors and drillers and engineers. But to see the utility side has some benefits as well. So the heat source variety is generic to the technology, but the scope of the project, being able to provide solutions to multiple customers at scale, is something that the utility is really familiar with. We're underground all the time, putting our pipes and wires there. There's also a diverse customer base. So this benefits a loop. You have a diverse load that provides different cooling and heating at different times. But also as a utility, we know what it's like to build an infrastructure, have the customers, build them, and have that network that works. So we're hoping to utilize some of that experience already and focus on existing buildings because it's much easier to put in this new technology in new construction. And we feel like for existing construction, it's essential because that's most of our service territory. And then finally, last but not least, is electrification. And if you're providing a customer with 50 or 60 or 70 degree water, it's much better than starting as an air source heat pump with whatever the temperature is outside. So that's reducing the energy needed and the number of air source or water heat or whatever type of heat pump you have reduces the amount of energy needed in those buildings. So this is the utility piece, which I will try to go quickly, which is just that we had 2 filings that we were required. And you'll see here it's summary of proposed pilot projects that we were asked to do in October. We were asked to do it in September, and we didn't have any. And we knew we wouldn't be able to make them up on the spot and didn't want to in a month. So we went out for a request for information, which is why we don't have specific projects today and why we'll be presenting and have a public filing to present those projects in about a month and a half. And then the second filing in January just dove a little bit deeper into the technical components that we're looking at, also more customer protection plans. So it's essential that those customers are being protected in however they're getting their heating and cooling that they already get, probably from natural gas, potentially from district steam or oil. And other pieces of there goes into what we assume the project cost to be, O&M, and various rate design methodologies. And again, this is all public. If you're interested, I'll just focus really here quickly on the fact that even a broad level, we had a consultant come and try to estimate how much these projects will cost, and specifically in Con Edison territory. Also the fact that we, would be paying union or prevailing wage, that there's already a lot of stuff underground that we'll have to work through, put our own pipes down there. The average cost per pilot project is probably going to be between 20 and 50 million. So we're looking for 3 pilot projects and a total budget of 110 to 130 million. This is the different buckets I think you can think of what we're thinking about. Please keep in mind that we're not, I think, mind readers, so we had to put these concepts out there before the RFI responses came in, but we're able to think about the learnings in terms of our service territory. So you have Westchester, so it's a little bit less dense. You have smaller residential single-family homes or 1 to 4 family homes, and you also have some commercial spaces. So that would be maybe C, less dense areas. And then you have large residential, that would be multifamily buildings in Manhattan or one of the boroughs. And then you have super dense high-rise buildings that have tremendous load, often are heating dominant, so we'll probably have some cooling towers on top, maybe have some data centers and ways to utilize that waste heat with or without boreholes as the solution. So we got our responses back in January, and we're going through them right now. This just shows where our electric and gas territory is. Because of the program and the way that Utendra was set up, we wanted to make sure that these could be gas customers as well as electric, both to benefit from the job side and also to provide some learnings. And all of that will be maintained. Yep.
The first slide showed, a wide swath of numbers of buildings. It showed a river and all that. Without getting into specifics, what is the size of these districts or these projects you're talking about? Is it several city blocks? Is it one building? I mean, just a sense of how large you're talking, because even 20 to 50 million dollars is like a lot of money for a very large project.
Yeah, and sure, I don't know if people can hear on the phone, but the question was what size and scale of these projects and how big are we talking about? Yes, I guess is the answer. So the most important thing for us is scalability. So we don't want to put the stuff in the ground and have it just be stagnant. Ideally, we would be able to find some ways to connect, bring in other customers and expand. And I think the question right now is, how big is too big right now? Just because it is a pilot and because we have a mandate to have some learning, some real substantive learnings in 2 years. I think we did get a variety of projects, I think without going into specifics, where it would be great to spend many, many, many millions of dollars. But I think those are 4, 5, 10-year plans. And so what can we do now between probably 2, 5, and maybe 10 buildings at the most, unless they're residential and much smaller, that actually we can wrap our hands around, have some successes, and then move on. So again, this is just very quickly, we own the project. The thermal energy network, that's the design, that's the loop. There's actually a slide next, which will kind of show that in a clearer picture form. But we have to operate and balance these. And this is brand new to us. So just showing that we do have expertise across electric, gas, and steam. And I think a lot of that will carry over into these projects, but a lot of this is new too. And that last point is that we want to and reserve the right to add loop in the future because of that scalability point that you mentioned. And then the only thing that remains the same is reliable, resilient, and safe, the way that we have all of our other utilities. I think you can see this I can move this down a little bit. I like this because it just shows a little bit more about what all the pipes and wires, where the water is going to be. So the pink are all of our customers. You can see there's a wide variety of what those customer types are. You also have a data center. In this case, it's actually just providing waste heat. So it's not getting any of the water, but it's actually able to dump some of that heat back into the ambient loop. Everything in the blue down is Con Edison owned. And so someone told me I have a laser pointer. I do. Okay. I don't know if you can hear me on the phone, but so these are the ambient loop systems. So this is where the water is going. You'll see this is some kind of boiler system. You also have, you can't see it here, but there's a compressor in here. This is a heat exchanger. And so these are overall balancing equipment because as a utility, we have to ensure that the temperature that we're promising and that temperature range that we're providing to customers stays within the range that they expect. And you also have a central pump house to help with the pumping of the water throughout the whole system, and then bore fields. So if we do drill some boreholes, which are going to be a lot harder to do in Manhattan than say Westchester, and then that can provide that heating and cooling as well. Timeline, we're at the little green line, which is we're deciding on what those 3 pilot projects are going to be. We're going to have a subsequent filing probably in April right now, early Q2. And then once those pilots are selected and approved, we have that money, we're going to move forward as quickly as possible. I do know that I think I'm not an engineer, but as an engineer, I think getting your hands onto actual specific projects is the most important thing, which we don't have today. But I did want to point out the Eversource pilot happening in Framingham, Mass, and that's with CDM Smith. The design phase is done. They're currently going out to bid, and that the construction will begin sometime in late spring or summer. So right now it's 45 proposed buildings. I think the website maybe is updating as they go along. So the majority of them are going to be residential homes. And the utility is going to fund that in-building work, and each house will also get some sort of ground source heat pump to supplement the water that the temperature they'll be getting. And I know we have a lot of folks on from NYSERDA too, so I wanted to call out the NYSERDA PON that started in 2021, and they've been able to fund a significant number of feasibility and design studies to get some of these projects off the ground. So, not waiting for this law to pass, but actually moving the private market forward. So we're very thankful for them, and actually some of the projects that received past funding from NYSERDA are interested in and filed with us for the RFI. So this is my final slide. This is kind of just where we are. Once we receive funding from the PSC, we'll be able to move forward. We're also building out an internal team. In my bio, it does say co-lead, but it's me and it's this guy, Greg, and it's just us. So we're not leading any people right now. And I think if we do get all the funding and all the projects we want, we're going to need to build up quite quickly. So really excited about that. Initiating all of that contracting, obviously, and implementation, and continuing our really important work with internal to the company and also external stakeholders. That'll be essential. And also pushed this law to get passed in the first place. We want to make sure we're staying with the intention and also think about where the utility can provide a really valuable role in the future. So that's my last slide. If you have any hard questions, I mean, John, you're going to take them, right? I think that's what, yeah, you agreed with? Yes. No, right here, second.
As far as I know, Con Edison is a T&D company, and they were divested to not be an energy producer. This is going to be an energy producer loop. How is the Public Service Commission looking at this?
The question is around Con Edison traditionally being divested and doing transmission, distribution, and how is this not the same as having a power plant? Is that sort of your question?
Yes.
Yeah.
That's my first question.
Okay. So I think that's interesting. In terms of the ownership model can be very different. And if you're thinking of a power plant or the generation of that energy, we're not tied to necessarily owning that borehole. So I think there's a lot of ownership structures that will work. More importantly, owning and maintaining that loop so that customers can feel comfortable when they pay a bill that they're going to get water between a certain temperature that they've.
You're an energy supplier now.
In these pilots, yes. Yeah, absolutely. And I think you're going to need.
No.
Oh,
you're
okay.
you're both it's working like solar. It's behind, it could say it's behind the meter energy production and using that energy. The data center is going to be dumping energy in. They should be getting reimbursed for that. The building that's taking the energy out should have a charge. How is this whole structure going to be working?
That's correct. Sorry, what was the question?
How are you implementing this?
Yeah, well, first we have to pick the pilots. Then the way that the rate structures will work is if someone who has waste heat is providing it back into the ambient loop, they'll be compensated for that. And that's why our rate design process is so specific and important. And then on the flip side, customers who will be using the ambient loop and water will also be receiving a bill to pay for that service.
Are you also interested in this program to try and get rid of the steam loop?
No, I think those would fill very different needs and are probably both essential to full electrification, or as close as we can get as a state and a city. Yep.
Similar question. Will you be doing network piping distribution networks on campus, which are behind the meter electrically, behind the meter for gas? For example, a very large college or university campus that has many, many buildings might even have a distribution system in place, but could benefit from such a loop. Will you do this behind the meter kind of application and own that piping network on the customer premises?
So question was around campuses, if those are going to be eligible. The short answer is yes, everything is eligible right now. And actually in the most recent filings, National Grid has proposed to do one, I believe at Hofstra, but you should correct me on that. So yes, all of those would be open as potential pilots.
Years ago, there was a company called Trigen, which was a New York-based company whose business model was trying to develop these systems. Ultimately, it went bankrupt. Was that looked at, and how does that compare to these type of systems?
I personally haven't looked at it, and I don't know if the folks that worked on the law have looked at it, and I think that's why it's really important to see if these pilots work. So if it doesn't work and the ratepayer is saddled with these, then this is not a solution that I think we're going to be able to move forward with for full electrification or even partial electrification. I think some of the hope, though, is that because the utility is able to scale and has all those customers, that you can spread the cost across a much larger rate base and provide a lot more value to multiple customers.
Doesn't the Public Service Commission have significant input in terms of how the utility is setting up their program?
Yes.
So that would refer back to what the comments relative to the fact that Con Ed is becoming a producer. You're following the rules based on what the Public Service Commission.
Yeah, absolutely. And every single very specific pilot has to be approved by all of the commission and in the intent of the order. Yeah.
And I apologize if I missed this, but through your RFI, the RFI is helping you select the 3 sites, or is there openings for others who may not have been aware of this?
Yeah, so right now, the opening closed, yes, but the RFI was for us to select those sites. We, per the law, can have, or per the order, can have up to 5 different pilot projects. And so right now what we're thinking, and based on some of the other utilities in the state, are recommending between 1 and 3. And that, we hope, allows us to start the learnings, and then we still have those 2 potential for the future that we may be able to slot in later and try to build out a diverse portfolio.
Thanks.
Yeah. Anybody else? Great.
If not, we should have time at the end for
Yeah.
3 speakers and have some good Q&A then.
Okay, let me just switch. I was going to look in that. I'm just going to check, see if people had questions. Can you see that up there?
Yeah.
Make this bigger. Okay, it's upon 4614, and Devetta, you can remind me if I'm correct on this, or maybe you know, John. That's the NYSERDA version of what the utilities are doing. Is that correct? I think, yes.
It's a precursor to what the utility.
Yeah, it's a precursor to what Con Edison is doing here. Okay, so this, and I want to introduce our second speaker, but I think what you'll see here, and what you heard a little bit from Caitlin, and what you'll hear from John, ties back into last month's meeting about metro electrification and I, at least for one, think that what we're hearing about with the UTEN, if I get those initials right, and this district geothermal systems that John is going to speak about is may be a big part of the solution to our decarbonized energy future. And so John Tesh is a project manager for advanced energy at CHA and has 20 plus years of experience in mechanical systems and fire protection engineering, specializing in high efficiency construction building systems. John's responsibilities include design of MEP and fire protection systems, and those included as well as energy auditing, building testing, and commissioning. John has designed for residential and commercial institutional clients and spent the last 15 years designing geothermal heat pump systems. And with that, I want to have John come up. Take it, yeah.
Okay. That's
and then forward back.
Hey, good evening. Can you all hear me well without the microphone? All right.
Probably just want to stay, we can hear you. So
Oh, I apologize. Correct. All right.
Yeah.
So thank you very much for that introduction, Fred. My name is John Tesh. I am not the piano player, but I am the drummer. I know. You got it. I'm here all week. Tip your wait staff. So I just want to thank you guys for this opportunity. Kind of a little bit of baptism by fire, as this was presented to me a couple weeks ago. But thankfully, I have done a presentation on this exact topic to a utility at the beginning of the month. So here we go. How do we make this thing move? What's that?
Just have to touch this screen, touch the mouse on the screen.
Oh, okay. I'm already failing. All right. All right, so in the course of this presentation, I'm going to try and, keep the moving parts down to at least these four, which are, after the introductions, we'll talk about our ideal projects, some current projects that I'm working on and the background of those, and then as well as, what's the end result, for all this very expensive technology, which is increasing on its efficiency, reducing our carbon footprint, and as I like to say, taking us off dinosaur juice, there still also needs to be a very feasible sort of impact that the non-engineers and the non-utility people can experience and understand. So New York State has aggressively established some carbon reduction goals to be achieved by 2050. We know that 40% of our carbon emissions in the state are from buildings. A district geothermal system or a district low grade temperature utility is a great solution to the peaks and falls of building energy usages, whether it's a heating dominating building or campus cooling dominant building, or even just a melange of usages, whereas business mercantile with an institution and then residential groupings. All occupancies and usages have very specific and unique energy consumptions. And it's very important that when you are taking a stab at designing and developing a district utility system, like a geothermal district, you need to be aware of what these peaks and falls are going to be and how you can absorb them and how you can manipulate them and use those energies to the benefit of the entire district. So municipalities, communities, and neighborhoods wishing to be a leader in implementing the Climate Leadership and Community Protection Act, this is a great opportunity for them to check off that box. And I think one of the best things to kind of describe is that by building equity or by improving and building and investing in the infrastructure of the area, you'll start to draw the attention of people and businesses and enterprises who want to come and spend money in your area, and therefore the municipalities no longer have to rely on that tax burden of the actual properties. You're going to start to have, a demand for a building in a certain location because of what is tied and connected to that building. So as we got a brief, history of that legislation And, excuse me. Oh yeah, am I still not doing well?
No, just wait.
All right. Y'all hear me? Y'all hear me now?
No.
Hello? I thought it just stay glued. I'll just stay glued. Okay. All right. So we're gonna talk about some ideal projects, and I heard it in the previous presentation. Someone asked, general question like, what sort of like scale or scope or size of a project are we looking for? Ideally, we needed 30,000 square feet would probably be like the entrance point of where we could, start to develop a utility. It's in order for a geothermal system to work, we have to have what's known as a balanced load. I mean, we can certainly drill enough boreholes or geothermal holes in the ground to match a specific load, whether it be heating or cooling, but we really don't want to go in a direction that's away from sort of like the balance point. For example, if I have a heating dominant building, would I drill more? Would I spend the capital to drill a geothermal bore field that is going to be of the capacity of the heating system? Or am I going to drill it to match that of the cooling capacity that I have in my building and maybe a little bit extra for contingency? And then through a period of ROI analysis, determine what sort of supplemental or high inertia heating source I need to compensate for that which the geothermal loop cannot cover. That's why it's important that we look at a broad range of usages, occupancies, buildings, and loads so that we can, start to employ what I call the load diversification. Hello. Okay. I also like to state that aging central plants are also a great primary candidate for this type of system. And the reasoning is because, like in the previous presentation, a bulk of the utility is already installed. Typical college campus or even a hospital campus, we've got either a high temperature hydronic line, supply and return, or we've got our steam lines with, sort of like satellite condensate return systems. You'll probably also have a campus potable hot water line, if not, in each building. So knowing that we've got an aging central plant that's, fossil fuel fired, its efficiencies at best we're in the 80% efficiency and dropping, not to mention the line loss efficiencies. We like to choose these sort of projects and then sell them our pitch. Like, hey, I could probably reuse what you already have here, make it better. And oh, by the way, we'll keep the fossil fuel plants online in case we need it. It works. All right. There's also a lot of things that go around in this in the sense of rules of thumb. People always want to know, well, I need land in order to get geo. So how much geo can I get out of my land? 1 acre of ground can typically yield about 400 tons of geothermal, or just about 500,000, BTUs of energy. This could get bigger. This could be actually upwards of 450 or more, but we as engineers like to, be conservative. And so this is a good running number that you can tell your friends about, and I think you'll be safe. I mentioned where projects where we have district load flattening can occur between the individual buildings. They're really the best candidate for these types of systems, and I'll explain to you more in the following slides. So geothermal districts are, for lack of a better term, a renewable source of building heating and cooling, plus a source of potable hot water. By using electrical, all electric devices to heat and cool, we'll reduce the amount of pollutants we put in the air for our unitary boiler plants or our campus boiler plants. And then, I also like to look on the other side of that coin too, which is what am I doing to the air during the summertime when I'm rejecting all of my heat into the atmosphere? These heat lenses or heat plumes too should also be, acknowledged as, in my opinion, a disturbance to the atmosphere. These systems operate at a much much higher level of efficiency. So there are significant savings on utility costs. You want to know, typically for a new construction residential, I can give you a payback period of less than 2 years. Granted, a lot of that is incumbent upon the federal rebates, the state rebates, and the local utility rebates. But the rule of thumb is if Geo costs 30% extra than your normal traditional system to install, usually that extra 30% is going to be recouped both through operating efficiencies and the rebates from all the programs. The savings on the utility are diverted back into the local government and community projects. And I believe, again, that you are going to improve the community, you are going to improve the area. People are going to start to come to either live, spend money, and or visit and vacation in these areas because, you know, it makes us feel good. So this is another little diagram that Kate had prior. I've just made it different colors and some other, some other little devices. So we got residential, institutional, multifamily, and educational. Typically for a U10 or one of these geothermal district loop systems, massive pumping power. I mean, massive. I mean, we have to constantly circulate that 50 to 90 degree Fahrenheit degree, temperature water. We have to just spin it around that donut. Okay, I call it, this is the primary loop in engineering terms. Okay, and each one of these buildings or clients or customers, they have to have their own series of electrically driven or pumps to pull off the donut. And see, either they're wrenching heat off the loop or they're putting heat back into the loop. And so typically the most cost spent on a system like this after the initial capital cost is the pumping power. Maintenance is generally 1% of your operation cost. What are you doing for maintenance? You're checking your pumps, but really you're just testing your water to make sure that its pH is where it needs to be, and you're adding antifreeze to it or water as need be.
Question?
Yes, sir.
Is it feasible to vary the flow rates depending upon the overall loads? I mean, a shoulder day when it's 70 degrees, presumably most of the loads don't need nearly as much flow.
Okay. That's an excellent question. So it sounds like, can we employ some sort of outdoor reset on the load based upon outdoor reset? And of course, because BTUs is nothing more than just what delta T across the volume of water that we're pushing. So we will gradually realize that people are using less and less energy from the loop, delta T, and therefore we will start to slow down the circulation in order to maintain that delta T. 50 degrees is the temperature you'd like to see for heating when we're making the loop colder. And then 90 degrees would be the upward temperature during the summer for cooling when we're putting heat back into, into the loop. Did that answer your question, sir? All right. So I work for CHA Consulting, and behind this ribbon up here, it says Clean District Energy Systems Example. So all right. Is there any way to do it?
Just pull the whole thing down to the bottom.
Like that?
Yeah,
There we go.
That's better.
All right. So currently I'm working on a project in Troy, New York, in the waterfront. What's the goal? The goal is to determine available renewable resources to be developed to maximize the amount of electrified heating to immediate surrounding buildings and areas. Wow. And Street Talk, my goal is to take a very specific amount of real estate wedged in between a road and the waterfront and put as many boreholes in it as I feasibly can so that I can have a relatively stable loop to give heating and cooling to 5 very different and very unique buildings located in Troy.
Yes, just touch the screen again.
Touch the screen, okay. All right. Again, Troy asked us to do this because of the waterfront, much like many waterfronts in upstate New York or in the New York area, Hudson Valley. That's where people want to spend their money. It's where people want to spend time. Municipalities want to draw people to the waterfront. So Troy is looking to invest in their downtown development in hopes of recouping their money. The significant savings of this development, I believe, is it's going to basically increase the disposable income of both the people who are doing business there, the people who are living there, because, you know, they're not spending, their energy rates are certainly going to come down. You know, if natural gas is $1.57 a therm, and these heat pumps are operating at COPs of upward of 5, we're looking at probably, you know, we're looking at what, 70% savings of your heating bill. In some instances, you know, that's a lot of money. I can currently say that I live in a very modern house that's very beautiful to look at, but not energy efficient. And I'm already on my 4th oil tank fill of the season. So, you know, things are getting more expensive and we need to get, you know, more efficient and more wise on how we use our energy. This diverts the revenue from the utility back into the local development corporation in Troy. Troy is promising to reinvest into its neighborhoods and redevelop them, make them more beautiful, and pick up more and more buildings on this loop. And this is also going to reduce the city's reliance on that taxes, which is the 3rd time I've mentioned it. And of course, as the New York State climate deadline looms closer, you know, more and more communities and investors are going to seek ways to try and to make this happen in order to avoid the penalty or the fines that will come. I had another slide here and I apologize. Legality, I wasn't able to really show it, but I'm very excited about this other project that I'm working on in Syracuse. Essentially, it's a rare opportunity where you have a project owner who's also a self-performing contractor himself, or he is the developer. So essentially up in Syracuse, there's a microchip plant that's being built, and we're going to start, you know, making chips and semiconductors. The property immediately to the next of it is going to be where the workers, it's going to be a community. It's going to be a planned development consisting of 17 apartment buildings or 17 buildings, all of them mixed use, meaning that the ground floor will be either some sort of institution, some sort of commercial or business mercantile entity, as well as the community buildings, a pool house, gymnasium, and school. I've noted here that I've got currently on the plan, I've got almost 1,300 apartment units, and one of them is in the courtyard style of 7 buildings. So part of what we're going to do is we're going to basically, if the groundbreaking is that core group of apartments, we're hoping to drill our entire geothermal bore field consisting of 430 holes at 490 feet deep beneath those buildings' footprints. Actually, they have an underground parking lot. So we're going to be below the parking structure. And in a way, this will enable us to reduce the footprint of our mechanical spaces because we are already in somewhat of a developed space. All of our pipes are coming out of the earth in this location. It's going to be a really nifty design and installation. The concept is that I have an unbalanced load. Those apartments actually have a greater cooling load than they do heating. So I'm starting to have, you know, probably around a third of a degree uptick per year of load imbalance. So as Caitlin was making mention, you know, these utilities have to promise an ambient loop, a loop that's within these temperature ranges. One way that I'm going to keep my loop cool is that we're going to do geothermal hot water, which is going to wrench the heat off this loop and then just turn that into your potable water or your shower water for that core group of buildings. Doing some math, I was able to determine that this is a good feasible solution to my warming loop. The penalty is the plant, the domestic water plant, is estimated to cost $1.5 million, or basically 5,000 megabtus of energy is what I needed to handle the daily water load of those core buildings. But, you know, it sure beats a cooling tower. It sure beats the pumps to send the fluid to that remote cooling tower all the way out there behind the shack, and the maintenance man who has to know how to take care of that cooling tower. So development, benefits, and impact. Renewable source of building, heating, and cooling, and potentially domestic hot water. I've told you that. We're reducing this proposed development's carbon footprint. Something else that I've learned in my design of these, another upstate geo project. The last thing that any planned neighborhood wants is to count the number of LP gas providers or fuel delivery men, or even like garbage providers, right? The people who pick up your garbage. So that was one of the challenges I had on this other project. And that's what they said. We don't want to leave it up to our tenants or our homeowners on who's going to be coming down the street to fill up their propane tanks or to fill up their fuel tanks. You know, this is something aesthetically that we're after. And believe it or not, that was a selling point for that development. So I brought this in here in part of my presentation too, because the reduction of traffic in your development will be felt when you don't have to have the need of people coming and replenishing your fuel storages. Reduces upfront costs and replacement costs of traditional fossil fuel fired heating systems. Less penetrations in your house, no more fuel lines, no more permitting for fuel storage tanks, no more NFPA 54. These are all great things. Improves air quality and public health. We're not discharging any of our waste heat to the atmosphere, nor are we discharging the byproducts of combustion to the atmosphere. This lowers the tenant overhead and increases disposable income. And this is another great thing. Like, this technology is very, very good. It's very, very efficient. And when designed and installed on a large enough scale, it's extremely affordable, if not more cost effective than other traditional HVAC systems. So, you know, it's definitely the way to head down. And then, you know, the threat, as the New York State climate deadlines lose closer, we need to get investors to see communities out there to make the switch over to avoid the unnecessary risks. Okay, I need to talk about something called load flattening. Load flattening is essentially the concept of where I have two substantially different loads with different peaks, and they occur at different times. For a standby system, we would hope to match these loads at that point in time, almost in a unitary way. But if we merge them together, those falls and rises, in contrast to one another, they start to flatten. And now we realize that we need to maintain a certain inertia in our loop or our load. We need to maintain that set point. And the pictures will show what I'm saying. So commercial buildings tend to have a cooling dominant load due to the inhabitants, all the electrical equipment that's in there, the lighting, and et cetera. The commercial peak loads are typically realized during the workday hours of 8 a.m. to 4 p.m. However, residential loads are often experienced in the mornings and the night. Okay, so two different periods of time. All right, the two very different peak loads allow the district geothermal system loading to flatten. So if the household is in the morning and in the night, and then in the middle of the day for the commercial, by joining the load diversification together, or these two loadings together, we're sort of making it more gentle, you know? And then we're hoping to look right around the middle where we got to constantly be creating this inertia or creating our capacity. So the advantage of load flattening is that the primary heating and cooling source is the ground heat exchanger, okay? This piping, it's a high density polyethylene plastic. Even 50 to 100 years is an underestimate. I mean, 300 years is literally what the manufacturer is telling us it's good for. Absorbed heat at no additional cost. It absorbs pressure. You know, it expands and contracts throughout the seasons. It's uninsulated, and low-grade heat recovery opportunities, which means I can scavenge heat from many different myriad of sources, blend it into my loop. I could also sink my heat in a many different myriad of ways, you know, by blending out of the loop. Disadvantage, of course, is that high capital costs. And what with the pandemic and the cost of fuel and you know, inflation, blah, blah, you know, it has gotten a lot more expensive. If systems were traditionally 30% more as compared to a traditional system, I'd expect to see that number be more like 35 to 40 now because of the drilling cost and the plastic. Space requirements. You got to be near a body of water. You got to own some land. You got to have the real estate, or else, you know, we just have to find another way to utilize the transfer of energy using this low ambient or low grade fluid loop. Requires to distribute heat pump equipment to provide heating. Yes. Increase in distributed maintenance. Maintenance is generally low on the loop itself. It can get costly when it deals with actually working on the equipment. This is refrigeration equipment. These are heat pumps. So the local HVAC man needs to be a refrigeration tech. And of course, as we mentioned earlier, the increased pumping requirements. So I'm just going to go over some system comparisons, just to kind of give you an idea, relative idea of scale. District air source heat pump. Those are all of those, your typical air source heat pumps, even the mini splits, they call them now, the little suitcase with the Mitsubishis and the hyper heats, air source heat pumps. Very common, very popular now amongst construction. In order to produce, what is it saying? 1,000 MBH of building heat, a district air source heat pump would cost us about $460. All electrical, our source is the atmosphere. District geo would cost about $390 for that same quantity of heat. On-site geo, meaning what I call unitary, a little bit less, but even the difference of $2 in scope and capacity shows how good of a technology this is. And then we don't even really need to talk much about the water source heat pumps, which is the boiler loop, cooling tower loop, or the natural gas fired hot water. You're seeing 20%, right? You're seeing 20 to 10 to 30% the cost of traditional fossil fuel with this all electric. Are there any questions on this slide? I want to be courteous to the amount of time I have, and I do wish to field some answers. Okay. Planning of a geothermal-based system. Finding the most balanced load profile. Understanding the loads and how they may complement. For example, cooling loads in the winter, heating loads in the summer. Identifying open space, greenfield parking lots, building sites for new construction, and then direct application or building system retrofit. I'll spend a little bit of time on this slide here because I think there's 2 points that have been mentioned earlier and I'm aware of as being sort of like tough nuts to crack in this field. So the first thing we'll talk about is direct application or building system retrofit. A couple of the pilot projects that we've bid or RFP to the utilities were with existing buildings. And I just want to say that thankfully enough, the unicorns in existing buildings are starting to go away. Like no longer are the induction units I see anymore. Even steam isn't really going throughout the buildings much anymore. It's usually coming into the mechanical room across a heat exchanger. People are working with hydronics now, chilled water and hydronics. So the ability for us to flip an existing building over to geo is relatively simple. An air handler can be repurposed just by swapping out its coils, its heating coil or its cooling coil. We can match them one-to-one with our own geothermal compressors. And now I've got all this added capacity for cooling and heating. One thing that I just wanted to state, I'm not sure if anyone's very familiar with it, but a heat pump simultaneously produces heating and cooling whenever it runs. There is a hot side to the geothermal heat pump as well as a cold side. So I'm making mention of this because you can literally make the energy for a cooling coil, for an air handler, for example, and then the heat that's coming out of your geothermal heat pump, which is very hot, 90 degrees or greater, that could immediately go into your building's potable hot water storage tank across a heat exchanger, of course. You could literally cool your cooling process before you have to re-enter into the ground. So that's why it's very important that you understand the loads and how they may complement one another. One of the pilot projects we did, we had a museum, a performing arts center, and then a visual arts center, an administration building. Yeah, an administration building. I think that was it, 4 buildings. And they were all on a high temperature, high pressure district loop. And this is, I'm making mention of this, this pilot project to the question before. So we've already got this, district loop, going out throughout the campus. We are going to essentially hope to use that district loop, keep it on standby in case the loop starts to get cold or not be able to provide enough heat. We can inject off of the high temperature loop into the geo loop across heat exchangers. Same thing for the campus's existing water, cooling towers. We can keep them online until we've proven that the system works or we've taken on more scale, that we don't need to reject that heat. So the adaptability of an existing building to be retrofitted into geo, it's there. And if anyone wants to argue otherwise, just listen and hopefully you're going to learn something because I've seen that it's very, very easy. The open space, greenfield parking lots, building sites, you know, we need good earth. We like to drill to 495 feet. 500 feet is the DEC no-no, and nobody wants to get into permitting to talk to the DEC why I can't drill deeper. I would advise against parking lots because that asphalt is a great solar collector. Doesn't mean you can't do it. Just be aware of what you're putting on top of your loops. Okay. The demand side. So this is a picture of just some of the typical HVAC equipment. That's a carrier chiller. That's an Aeon, I don't know, rooftop package unit, ERV. Heat pumps, they pump heat uphill. That's why they got that name. They move heat in either direction. So we've got heat pump chillers, which, you know, a chiller tends to make your 45-degree water for your cooling system. We call them reversible chillers now because, you know, they can make now that 100-degree water. We've got terminal heat pumps. That's just it. That's the high stacks in your hotel here in New York City. That's your sort of like under the window fan coil. You know, there's a compressor in there. You can have heating or cooling at any time of the day or year that you want because a compressor, that's the heart of the heating and cooling system. Water heat pumps are domestic water heaters, which just takes the geo water and runs it across a heat exchanger, compresses it higher, runs it across another heat exchanger. I'm being really nerdy right now, and I apologize. Water source, water air units. We just directly convert the geo energy from the ground loop into the air. Water cooled chillers, another thing we've talked about, and then this one right here. This is kind of, how do I say this? This is your high efficient mini splits, your Mitsubishis, your hyperheats, but now you can connect them to a geothermal loop. So all the benefits of inverter compressors and modulating compressors and match loading, hot gas bypass reheat, all of that can be done now on a geothermal loop, which will really, really open doors to the existing building retrofit. And I say that because the VRFs of the world now are already being used to retrofit buildings, and we're just plaguing rooftops and the grounds with the outdoor units. Now we can literally bring that indoors, and you can have like 156 of these cassette units on like one compressor. Everyone's got a thermostat or a control in their hand. It's definitely going to make things a lot better and a lot easier to get geo in the building, in my opinion.
But yeah, you had a question out here.
Yeah.
With the VRF Geo,
Mm-hmm.
you potentially have no water anywhere in the system. The refrigerant is literally going underground and to the ultimate.
No. Okay. So what you've just referred to, sir, is known as DX geothermal or direct exchange. And that's a refrigerant loop. You know, the compressor is pumping it to either to the evaporator, condenser coil, depending upon function. And then that same compressor, unfortunately, is forcing that refrigerant all the way into the ground and then back up. I've designed those systems a lot. This is not what we're talking about. Those are great systems. I call them high inertia. And what I mean by that is that because it's direct exchange and the refrigerant is in direct contact with the ground through copper pipes, that startup, the ground literally is going to have to play catch up to the compressor because it's so efficient and it's pulling the energy so rapidly out of the ground. And that's good. I'm making the ground immediately colder.
In your loop.
And your compressor starts, right. So it's very important that when you choose that type of system, which is great. And by the way, they cap out at 5 tons. There's no manufacturer who makes a direct exchange compressor greater than 5 tons using, R410A. Yeah. But what I thought I was hearing in your question, and which I would like to focus on, is the VRFs with the refrigerant. That's the gambit. That's the win for geo, because in a retrofit, it's easier to install line set than it is, supply and return rigid piping. And that's why these mini splits and these ductless splits are all the rage, because it's just soft copper tubing. The geo compressor is the big module. It's in your machine room. It's connected to the earth. And then after that, it's just refrigerant line set to a branch box to all the heads. So the fact that that technology is now coupled with the earth will blend these two sort of mechanisms, if you will.
So in theory, you could have one compressor serving an entire building, with each individual load individually controlled. In theory.
In theory, yes. For the selling point, yes. In theory, you could have one bank of VRF geothermal compressors driving thousands of remote individually controlled units. Yes, sir.
So you're offering a building condenser water, but not hot water, chilled water. So they would have to condense their heat pump equipment, but they couldn't purchase hot or chilled and add hot or chilled to their systems, their building loops?
They wouldn't need it.
Are you in reference to the VRF scenario?
Yeah.
Okay, well, the VRF scenario, okay. VRF heat pumps are simultaneous heating and cooling heat pumps. We called them the chiller killers back in 2007, showing my age. And the concept is that rather than having to have these chillers, because most buildings, we've got the core, which always needs air conditioning, and then the perimeter loop, which may need heating or cooling depending upon the season. These were invented so that we could basically wrench the heat off of our core and then immediately put it in the perimeter without sending it back to your plant, without having to pump that energy back down to the plant and convert it over to the other side, you know? So yeah, you don't have to buy that chilled water. You don't need a chiller anymore.
Okay. I think what we're talking about here is connecting the geo. You need additional energy on top of that. No, I think because those VRF systems exist, but now tonight's topic is when you need something other than moving it from the core to the perimeter or perimeter to the core, get your free earth energy as your source.
Right. That answer your question, sir?
Gotcha. Thanks.
But we can talk more at the end. Any other questions? All right, I'm going to quickly go through the borehole. As I mentioned, we typically like to go down to 495 feet. There's no reason not to. Ideally, I'd like to see about 2 to 2.5 tons per 500-foot borehole. Everything's dependent upon the geologic formations, not to mention groundwater migration. But we've got what's known as the pre-manufactured U-bend. I do not like that feedback. And then it's just supply and return, guys. Typically on the, what? We like to see 5 feet separation between the supply and return so we can keep inertia, transfer of energy. The annular space of the hole is filled with a bentonite grout or a cementous grout. So that it's just basically a solid plug. And we always like to stay below the frost line. My rule of thumb is always 5 feet, regardless of the 42 inches that we have in this area. I'd like to see about 6 inches of clean soil above and below my pipes. Most drill rigs that do this work are well drilling rigs for potable water. So they're tooled for 6 inch. If you can find a 5 inch, great. Nobody's ever given me a rebate or a discount for using a 5 inch bit. And I've used even 3 inch bits as well. There's a perfect tool for every application, and I rely on my drillers to give me the feedback, and I respect them as the professionals of doing it. 1.5 inch piping, that's kind of a little bit on the large scale. I probably see 1.25 inches on a borehole like this, but I may use 1.5 inch. Typically for residential, you'll always see 3/4. Any other questions? Sorry.
So these boreholes, structurally, do they tend to act as a pier system?
No structure whatsoever.
None.
Nope.
Because you said you were putting them underneath that apartment complex, which could affect foundation, but you're not casing, you're using a cement. Is it one that'll withstand acidic groundwater?
Acidic groundwater?
any type of corrosion because
What-
limestone will corrode.
Okay.
So if these go in there, could cause weak spots in the foundation.
Well, we're not connected to the foundation, and our bore field will of course have to be coordinated with the other, consultants, structural, and the site. But my experience is that we want to be no less than 10 feet. More than 10 feet is always greater, but I'm more concerned about the thermal penalty. Like, what can the energy in this loop do to the foundation and or vice versa? I've read of some installations where the loop field was so close to the foundation that they were actually conditioning the foundation. They were losing energy to the foundation. So without speaking out of my league, I would say that our typical borehole spacing is 20 feet borehole to borehole, which means that we've got 10 foot of radius. Okay. If I settle on 15 feet and I get buy-in from my structural guy, that I'm not going to have any effect on what he's doing with his footings or his pylons, then I'm good to go. Okay. The bentonite grout, it's not as caustic as like cement. And the fact that we're using like really just plastic tubing here, there's no real reason to see any sort of caustic elements or any corrosion.
Well, it's not the caustic elements from the plastic to the cement. It's from any environmental effects from outside of the cement.
Okay.
So you go into, say, Florida. Florida is large limestone area.
Yeah, it's got a 3-foot water table. Born and raised before there was a Florida man.
Yeah, but that area, you could have your limestone foundation basically eaten out from under it.
Oh yeah, and sinkholes.
Yeah.
Well, that's true. Typically in Florida, because of that water table, it's either an open loop standing column well, or they do that GODX, which has its own corrosion issues because they use copper pipe. I think I like your question. I haven't experienced anything like that or even a question like that in my past, but my answer is I always get buy-in from the people who are smarter than me involving things like that. So that's where I'm at, but thank you. Any other questions? Okay, ground heat exchanger sizing. This is the bore field. Manny mentioned annual heating and cooling loads will affect the overall size of this bore field. The peak heating and cooling loads are very important as well. Bore spacing, grout conductivity, ground temperature, and the approach temperature. So peak heating and cooling loads are important in the loop design because it has a lot to do with load flattening as well. Just because your building may experience on January 12th, that massive sort of heat loss, doesn't mean that you have to design for that actual increment of massive heat loss. By grouping these buildings that have a diverse heating and cooling load, who experience different peak heating and cooling loads, we're flattening it. We actually have the investment in the ground that it is of the adequate capacity and size to produce the inertia at that moment in time to cover the loads. A lot of people tend to get caught up in those peak heating loads and think that they need to, kind of like what we used to do as engineers, traditionally design for the cooling design day or the heating design day. So now I've got this boiler that's rated for 400,000 BTUs, but I only need 400,000 BTUs 3 hours of the year out of 8,760. That's the kind of approach or the concept that I'm trying to explain. You don't need to invest in that peak. You can rely on everyone else's loads to help flatten and soften those peak demands. Bore spacing, I mentioned, I don't like to go less than 15. You're allowed to go as close as 10. 20 feet separation is the sweet spot. And the reason is just the interference of each borehole with one another. The rule of thumb is the ground is always the eye of the needle, okay? The ground can only give up energy and absorb energy as fast as it can. Okay, you can't expect any more out of the ground. So do not design your system that will exceed the capacity of the ground. Grout conductivity, 1.2 is pretty much the typical. Don't buy anything less than 1.0. But again, If your ground has a greater conductivity than the actual earth it's connected to, what are you doing? Ground temperature, we know that the average temperature around here is 53 degrees. The swing is minute, maybe dips down into the high 30s on a natural sort of occasion. This is a very good temperature for geothermal. Any questions? Yes, sir.
When you're modeling multiple buildings and trying to load flatten, what tools do you use?
I use design build. And I also use DOE design build. So where I'm at right now, I'm the dirt engineer and engineering this loop. CHA Consulting used design build, which is a DOE2, sort of like a blessed program, if you will. And just using all the tried and true values that the Department of Energy has developed for the different type of buildings, both for periods, ages, and usages, it spits out these sort of like not to exceed loadings out of the 8,760 hours of the year. And then that's where we find it. We find that peak, we find that peak day. And then I'm curious about the peak load, the hours before it and the hours after it. And then I put that into my loop designing module. Thank you. I know I'm speeding up. All right, I'm getting the evil eye that we got to make this happen. So, and like most system types, in addition to peak design, loads, the balance of the loads on the GXX over time is a critical component. I'm seeing, 15 years, my Earth is gaining 3 degrees of temperature. We don't want to, find ourselves having to deal with a warming Earth. Undersized systems, unlike most system types, in addition to the peak design loads, the balance of the loads on the GHX over time is a critical component. So what we're showing here is maximum and minimum water temperatures. You can see that this loop, it's hot. This heat exchanger is hot because over time, 20 years, pretty soon my Earth was now like 105 degrees. And, here's where we started. So no bueno. Bore field drilling is a messy process. So is construction. It's just not pretty. Just a bunch of well drilling rigs out there, just putting holes in the earth, making lots of noise with the compressors. You'll experience spoils of water, dust, and even dirt, but construction mitigation, we'll take care of that. Ideal borehole spacing. I made mention that we'd like to have 20-foot spacing. This is a very nifty graph. I don't think we've got enough time to really get into it, but the point is more separation increases the overall. More separation increases the overall capacity, but you have to have the real estate in order to experience that. And one thing I just want to quickly talk about is every geothermal design has to have a thermal conductivity test. And what that is that we drill a borehole 495 feet, we put an 1.25 inch loop in it, we grout the loop. And then we hire this guy who's basically got a fluid heater and he measures the temperature of the loop, and then he turns his machine on, and then he just starts logging. What is the loop temperature? As I'm putting energy into this fluid, how is the ground responding? And over the course of 24 to 48 hours, in conjunction with the driller's log, they create the thermal conductivity test, which then tells us, what's the diffusivity of the ground? What is the conductivity of the ground? It gives us an idea, or gives us our mathematical elements of how much heat the ground can give up and how much heat the ground can absorb in a finite amount of time. Down here, this used to be 15 to 20, but based upon the recent pricing that I've been giving, I've had to increase it to 20 to 25. So, already we're seeing, upticks of 20% in what our costs used to be.
What was that? I'm just going to hold questions.
Yeah.
But just use the term that I don't think most people are familiar with. Diffusivity.
I know. Diffusivity. You said it. Did you say it? Diffuses?
The rate at which the heat can diffuse through the air.
Can't say the word, but it's
just, you repeat that.
It's the rate at which the substance can diffuse the heat. I'm sorry, guys. Can you blame it on me being a drummer? Hybrid solution. So hybrid is just a term that I like to use for it just means like, it actually means traditional. What traditional component of a heating and cooling system do I need to bring into this geo system, making it hybrid geo so that it works? And I either need a source of inertia, I need to put heat into the loop, or I need to remove heat from the loop, i.e. a cooling tower. That's what that means. Here's my project in Troy. They really didn't even give me, and you know what? Over here is like a war memorials, like really like, they just put some really nice eye candy so close to where they tell me I can drill. And this is just gonna be, it is a parking lot now, and it's gonna stay a parking lot. Everywhere where you see cooling tower, those are buildings that I'm picking up. So that's my building, that's my building, that's my building, and these are my buildings. We're hoping to provide heating and cooling and potentially some potable hot water to all those buildings in that grouping. And if this turns out to be something successful and it works, which it will, they may allow us to expand, and we may just go down the river, or we may drop a couple of Slim Jims or plate and frame heat exchangers in this river. This is the project that I'm currently working on in Troy. As you can see, this particular project is a heating dominant in the sense that over 25 years, my loop has gotten colder. The earth has gotten 3 degrees Fahrenheit colder. This is just a projection, and this is just based upon the existing systems or the existing performance of those buildings. If any of these buildings were to receive some sort of envelope renovation or modification, our loads would only get better, meaning that I could take on greater capacity. That's, I spent a half a day this is basically my bore fields from within the module. I think it takes a special sort of like skill to be able to stare at this polygon shape and figure out, the perfect combination and spacing of these boreholes, because I know how many holes I need to get into that earth. And so that's the challenge. Just real quick, this is 20-foot spacing, 15 and 10. That was the spacing that we had to do for this project. Yes, sir.
Can you go back one slide? I thought you said over the lifespan, the ground temperature would go down 3 degrees. Can you explain that a little bit? Or maybe I misheard that.
Well, right. So it's a simulation. We are removing more heat. We're in a slightly heating dominant sort of system here. These buildings require more heat than they do cooling throughout the course of the year. So as we're, okay, a heat pump works much like your refrigerator does, in the sense that you put things inside it that are warm and they become cold once they're inside it. And the back of it is where the heat is rejected. So if I can even just freeze this ground, I can just drop it in temperature. The heat, the delta T, or the drop in temperature of the ground, means that I'm grasping heat and I'm wrenching it out and putting it somewhere. I'm literally just slowly over time cooling that ground, asking it to give up its thermal energy and never replacing it. And nowhere in the model did we see, a diversity where, cooling may be picked up, and we can now re-inject that heat during the summer months so that we wouldn't have that gradual cooling.
So I'm hearing normally you do 8760 per year, but actually you're doing, I'm doing a lot more than that. I'm doing 20 years to see,
oh yeah.
Heat away, or in this case, cooling up the earth.
Absolutely. Okay. Absolutely. You always want to do a projection. Yes, sir.
Roughly how many square feet the Troy project is, like building square feet?
Hundreds of thousands of square feet. I don't know off the top of my head. And I thought it was a funny joke, but typically where I'm being used at CHA right now is I will review the building calculations for gut checks. Just finding things that would stick out. If I knew, if I could detect them, then I know something was done wrong in the calculation. But I try and stay in the dirt, and in order to make the loops work. But well over 100,000 square feet easily. And, if you like, I could even, give you that answer probably tomorrow if I have your sign-in sheet to let you know. Any other question? I know I'm trying, Fred. Okay. Pros and cons, air source heat pumps. These are the most popular. They provide electrified heat. They're more efficient than electric resistance, which is 99% efficiency. It's a good solution if the balance is there and not the peak capacity. What does that mean? Typically, people around here, they buy a heat pump, they size it for heating, which is oversized for cooling, so they actually bought more heat pump than they needed. Cons, limited market availability at district sizes, large footprint, and 2 has a peak capacity at low ambient. So what does that mean? When I need the heat the most, it's the coldest outside, and that air source heat pump is not working as efficiently when it's cold outside. You typically have to bring up auxiliary or backup heating elements anyway. So now you've got 2 heating systems in effect. And of course, the very large electrical service requirement. Lake River effluent, I would say the pros, it's geo. So it's got all those pros. The cons are not a lot of people are happy about you dropping plate frame heat exchangers with a glycol solution in their bodies of water. I mean, you can argue till you're blue in the face, but there's always someone out there that's going to say, what if? And you just can't pollute New York waterways anymore and get away with it. Electric boilers, I'm not a fan of electric resistant anything because, it's just 99% efficiency. It's electric resistance. But when it comes to boilers, they are a better alternative to any fossil fuel boilers because I don't have to have fuel storage and I don't have to have a chimney. My conclusions. So likely solutions include diverse use of localized geographical areas. That's your real estate. That's your water bodies. Wastewater heat, I did not get into, but it is out there in order to expand the system capacities. Capacity becomes an issue when load flattening and load diversity cannot be accomplished. That means that you have to deal with those peaks and falls in a standalone, isolated moment. And, it kind of goes against how we formulate these systems. Hybrid systems may be the cost-effective solution. Exactly. Life cycle cost analysis should be performed against all proposed systems. The LCCA, as you know, how much does it cost to build the thing and how much does it cost me by the time I'm throwing it in the dumpster? Summary, understand your load profile. Look for synergies. That is, look for ways to either grab heat or dump it somewhere. Maximize the use of your open spaces. And then the district loops open the options for sharing and supplemental energy. And what does that mean? That means that that museum on that campus, which requires all that awesome temperature control and humidity control and year-round cooling, it's making free hot water for the dormitories on the other side of the campus. All right, my name's John Tesh, and I'm the guy on the right.
Yeah. More or less. I think the line. Yeah. Okay.
Okay. Oh, this is working. Okay. So Bob, you can use either one of these. Just let me switch presentations here. And we'll hopefully have a few minutes at the end for Q&A. And I'm just going to, Bob, if you don't mind, I'm just going to skip the formal bio. Bob Berninger is Director of Plant Operations and Energy and Engineering at Memorial Sloan Kettering Cancer Center. He's been there for 17 years. Before that, he was with Columbia University as Assistant Manager of Physical Plant. I've had the pleasure through AEE here to know Bob for many, many years. And I will just tell you that back in 2016, when AEE named Bob as the International Energy Manager of the Year, that was a very well and long-awaited honor that was bestowed upon him because something he earned. I've known plenty of folks in Bob's position throughout my career, and he is literally one of the very, very best at what he does. With that, I'd like to have Bob come up here and talk about how not just geothermal, but how district systems can help cut our energy footprint as well. Bob.
Yeah. Just, oh, sorry, touch the screen with the mouse.
So we've been hearing about district energy, basically mostly on geothermal this time around. But I stole this from what is a district energy? I stole this actually from Danforth. I mean, I'm not gonna lie. But district energy is just using energy from multiple buildings, be it heating or cooling. A little bit about Memorial Sloan Kettering that I'm overseeing. It's located on the Upper East Side, and it's what we call the main campus. The 7 interconnected buildings of various vintages and various states of renovations. The oldest building was built in 1938, and the newest addition was in 2006. Flanking the main campus, which is a full city block, we have the Rockefeller Research Lab, which was built in 1986, and the Zuckerman Research Center, which was built in 2006, and then added on to in 2010-11. So we have that. They're all interconnected. As you can see, this is a shot from our BMS, our stacking diagram. And you can see I've got the buildings, and every floor is something different. I have laboratories, I have office space, I have medical offices, I have MRIs, Linacs, CAT scans, what else? And hospital, patient care. So it's quite interesting, and working with everything, it gets quite interesting. Prior to 2020, we were heated by Con Ed steam. We had 3 points of entry for Con Ed steam, one for what we call the main campus, which was the full city block. The 2 lab buildings also had their own points of entries. Steam was delivered at 125 PSI. Was used for domestic hot water, reheats, sterilizers, washers, and steam turbine driven chillers. We took that 125-pound steam, dropped it down to 70 pounds for our sterilizers and washers and other process loads. And then also took that steam and dropped it down to 5 to 12 pounds for domestic hot water, our reheat systems through shell and tubes, and our steam preheats in air handlers and humidifications. And then we had steam turbine driven chillers using steam at 125 PSI. With that old system, it was wasteful. It was costly. So in about 2016, we said, what can we do? And we went into design of replacing the steam system with a hot water system. Overall, the project was 6 years in the making, 3 years worth of designs and permits, and 3 years of construction. We ended up buying prefab houses that we ended up lifting up to our roofs, and we had 2 boiler plants. One of the boiler plants from Memorial Hospital had 12 boilers. 4 of them were dual fired because we needed a secondary fuel source to provide heating for the hospital in case we lost natural gas. Now, what are you going to say about what happens to all the other buildings? We were just going to be able to shut them down, button them up, and pray for the best if it was an extended gas outage. In the Zuckerman building, we had 9 boilers installed, and also we added cogen. The original design was 4 units for the main campus for the Memorial building and 2 for Zuckerman. But when we got into design, structural couldn't handle 4 in Memorial, so we flipped the 2 over to Zuckerman because it was a newer building. The project was in a building that was still occupied, still running. We ended up putting in over 30,000 feet of piping in 2.4 million square feet of spaces. We figured out different ways. I mean, I was crawling all over the place trying to figure out different pathways for piping. We were renovating a floor. We're like, oh, let's run piping through this floor so that we don't have to come back after the floor gets renovated. Other things that we did is for over 20 air handlers, we ended up ripping out the steam preheat coils and putting in and just connecting hot water to these air handlers using the chilled water coils. We heat the place with 60-degree water in those coils and deliver 58-degree air to our spaces. 115 air handlers, we ripped out the preheat coils and put in new preheat coils. And 3 of the air handlers, we had heat recovery in those units, runaround coils, heat recovery. So instead of putting in new preheat coils, we just inject a little heat into that heat recovery system to provide what we need for those air handlers. There were 15 domestic hot water systems installed, 40 heat exchangers that were converted from steam to hot water to hot water with new plate and frames. And we also installed 8 new adiabatic humidification systems for the humidification that we required for our patient care, our ORs, and our vivariums. Now, this is the hot water flow diagram, and you can see it's quite large. I actually had this drawing up on my wall, but it was actually as big as the TV screen, and then you can see it, but on the screen you can't really see it. So, I mean, it's just showing you the complexity of doing this. Here you see our new boiler house that we put on top of the Zuckerman building, and on the side you have a couple of the boilers that we put in. Another view of the boilers from the other angle, the pumps. This is yes.
Just go back 2 slides.
2 slides.
Everybody, just point out what's on the left-hand side there.
So this is the boiler house here, and these boilers are inside this house. These radiators are actually our dump radiators for the cogen generators that are sitting in the back here. Here you see the individual stacks for each boiler, and here are the stacks for the cogen generators. This is a view of the pumping skid for the heat recovery off the engines. And here's a picture of one engine, and another view of the 2 engines in one spot, and another view of the side engine. So that was my hot water system. Now the chilled water system back in 2008 was 4 independent chilled water plants. Altogether, we had 18,600 tons of cooling capacity, but the problem is that it belonged to each building. If I had a problem in the Rockefeller building, and the year before I started there, they lost 1 chiller for the summer, they were short 1,000 tons of cooling for the summer on a 100% outside air building. It kind of hurts. In 2008, we went into design and interconnected the 4 separate chilled water plants. The main campus had a primary, secondary, tertiary system. So on each system, we ended up losing about 2 degrees. So by the time we got to the last building, we're producing chilled water at 42 degrees in the plant, but by the time it got out to the building, we're at 46 degrees. And the engineers who had built the building designed the chilled water coils for 44 degrees. So you were already behind the game. So we did the project, interconnected the plants. We eliminated 17 tertiary pumps and 4 primary pumps, lowered the overall demand by a megawatt of power, which the institution used right away for other renovations and ORs. But now we dispatch the chillers from the most efficient to the least efficient. Our load varies from 500 tons in the winter for process loads to our peak load last summer was 11,500. And we're also able to participate in demand response because I have all of these chillers on standby. I can flip over to steam chillers and reduce the overall demand by about 3 megawatts. One of the other things that we found with the steam to hot water conversion is we actually reduced our tonnage this past summer by 1,500 tons. We no longer had leaky preheats. We no longer had leaky steam traps or any other things, and we were on top of it. But one of the things that we found, and I didn't put this on here, is that a few of the air handlers where you'd go around and test the traps and say they're cold in the summertime, they were still leaking by a degree or two, which most of us would throw off as calibration error. It wasn't. Once we turned the steam off and cut the pipes, the temperatures off the reheats became the same temperature as the outside air. So that 1 degree, 2 degrees was really 1,500 tons worth of cooling that we were doing, and 1,500 tons worth of heating that we were wasting. Here is a picture from one of our systems showing the various plants. The Zuckerman plant, the infill plant, the Rockefeller plant, and then the Memorial plant. When I took this picture, we're only running the infill chiller plant, and we were running that because our ORs needed 42-degree water, and free cooling was not doing it anymore. This is a picture of our chillers and our primary chilled water pumps. Looking down chiller aisle, there's 6 pumps, chillers in here. Our condenser water pumps. A couple of different views. Plate and frames here for a hydraulic break between the 2 major buildings. Because one building is at 450 feet, the other building is only at 300 feet. So we just needed to break between the hydraulics to prevent pipe rupture. Now, I'm just comparing 2020 to 2022. You can see the electricity usage, gas usage, steam usage in 2020. And we were at 336 kBTUs per square foot at that point. In 2022, after the steam boiler plant came online, steam was reduced by 80%. We still need steam for steam turbines and our process loads, but we're down to 80%, using only 20% of that. And of that 20%, 10% is being used just to keep our pipes hot. Overall, between 2022 and 2020, our energy usage was reduced by 17.8%, and our GHG reduction was 21.1%. Now that's using ESPM, Energy Stock Portfolio Manager data. That's it. Any questions? Please ask questions.
What is the temperature of the hot water distribution?
So the hot water distribution, we're running it at 180 degrees and returning it at approximately 120. We're still tweaking it in, but it's to change my staff's mentality. It takes time. On that 60-degree day back in, I wasn't here. It was a nicer day, but I'm talking to my staff and they're like, well, we don't have enough heat. We dropped down to 173 degrees. Well, 173 degrees when our heat exchangers for reheat and our domestic hot water is 140, we still have enough heat. It's just the mentality that my staff have that, hey, we're producing at 180. We need to be 180 all the time.
Can I ask a follow-up? So yes. With all the electrification, you're at 180, slightly higher than what a heat, the best.
Correct.
What's your opinion of further steps with electrification?
You know, it's baby steps. When we started this project, talk of electrification was just beginning. MSK really was the last project that NYSERDA funded for cogeneration. You know, we went ahead and all of a sudden, like, oh yeah, we're not going to do cogeneration anymore. It's, you know, gas is bad, cogen is bad. But in my opinion, switching to a hot water hydronic system gives us the possibility of the next step of matching the chilled water plant with the heating plant to do electrification. If I converted all these hot water boilers to electric boilers, I'd need another 25 megawatts of power. Now that's doing straight electrification of the boilers. My chiller plants, they're 20, 30 years old. They're still working because we maintain them. But I've actually started the next phase of this, and I have a kickoff meeting tomorrow for next decarbonization of the whole system to see what our next steps are. The institution also has what?
I was gonna say, go back one slide, Bob. And just, if folks look at that, and maybe you should say this, look at the last two numbers that down there. So just tell the people on the bottom, on the online what we're talking about.
Oh, we're talking about what the energy reduction was just by converting from steam to hot water for the 2.4 million square feet at MSK.
And Bob, point out, if you don't want to toot your own horn, I will.
Bob did this, that 21% reduction in or 18% reduction in energy and 21% reduction in greenhouse gas reduction is, you all have to remember that Bob's buildings are already about the most efficient buildings you'll ever see, and maybe talk about where the percentage we talked about the other day, where you came from when you first started.
So when I first started at MSK 17 years ago, you know, we just baby steps. First, we went after the chiller plant, then the chiller plant, then we interconnected everything. Then we went after the air handlers. We did air acuity to do demand ventilation control. We're able to take the ORs in off hours, unoccupied, from 25 air changes down to about air changes. And with air acuity, we were still able to do to make sure that the rooms were in ready state. But we've also put them into the vivariums and our labs, where the vivarium, we were able to take the air changes from 15 down to 8. In the labs, we took them down from about 12 air changes down to 3 and 4. And most of the labs now are thermal driven instead of just ventilation driven.
And Bob,
yeah,
came down 40% from.
So yeah, overall since 2007, we're down about 40% in energy usage overall for that 2.4 million square feet. But yeah, it's been a fun job. Questions? Yes.
Here's a question from an online attendee. The question is, can you elaborate on the demand response aspect?
So on the demand response aspect, because my peak load is 11,000 tons and I have 18,000 tons of cooling, I have 9,000 tons of steam driven and 9,000 tons of electric. During the peak demand, when Con Ed or NISO calls a response, we'll actually start up three idle steam machines and shut down 3 electrics, and thus we're able to reduce our peak demand by 3 megawatts. Because each 1,500 ton chiller is about a megawatt of power to run at that time. Yes, sir.
How much of the distribution piping were you able to reuse versus completely having to rip it out?
The only thing that we reused was reheat water piping, because that was already there. We just
use the steam.
Couldn't use the steam because we still had to keep everything running. And because we received Con Ed steam, we had no real condensate return. Condensate from the air handlers, the reheats, either went to a collection, depending on the building, went to a collection tank, and then we reused that water for cooling towers, which is very corrosive, but that's another story. Or in the older buildings, it was brought to a quenching tank, quenched, and dropped down the drains. Yes.
Another question from the online attendee, probably to all speakers here. Given DOE no longer have funding for the professional training programs regarding, technology training like this, for those technologies, what resources or workplace replacement programs are available for emerging professionals like undergraduate students or young folks out there?
So MSK partnered with NYSERDA for workforce development. So we trained all our plant operators, and I think we did 30, 40 plant operators went through the system for building operator certificate course, level 1, 2, building retuning. Did I do another one? I can't recall. I'm sorry. But that's that. The other things you can do.
Money in the IRA.
There's also money, the Infection Reduction Act. There's workforce development from NYSERDA. There's AEE, there's ASHRAE, there's ASHE. There's just so many different groups out there that are doing training. It's that you have to be able to go out there and you want to be trained. It's not going to be spoon fed to you. You know, that's the thing. Yes.
If you're interested in customized operations and maintenance training, talk to me. Devetta Thatcher at NYSERDA.
Yes. So one of the things that was just said is if you're interested in the customized workforce development training, please reach out to Devetta Thatcher at NYSERDA. You can actually go to the AEE AENewYork.org website, find Devetta's email there, and can email her directly. Yes, sir.
When you did the steam to hot water conversion at the air handling unit, you said you're using chilled water coil now for? Yeah, so there were a bunch of air handlers that we ended up reusing the chilled water coils for heating. We ended up putting, so on one floor, we ended up putting an isolation valve on our chilled water supply line. And then we would close that valve, and then we would circulate the water for those air handlers, and then would inject heat through a plate and frame to provide 60-degree water to the air handlers. We've never really risen that water higher than 62 degrees for those coils because those cooling coils are huge. They were 10 and 12 row coils that had a lot of heating. Now, the thing that you have to worry about is that you need to make sure that your velocity through the coils is high enough that you don't freeze. And yeah, we froze a coil, but it was a manufacturer defect. After the fact, we froze a coil, took the coil out, and we're trying to figure out why we froze that coil. And we found out that when they did the U-bends, they put a U-bend supply to supply and a return to return. So that leg, I had a dead leg in that. And with 100% outside air handler, we froze. Now, that was the very first season that we did it. That was in 2021. In 2022, with the 60 degree nights that we had, we froze one outside air curtain. And we're still trying to figure out why we froze that one, because doing thermals on the coil after we fixed it, all the flow is good. The water coming out of the coil was at 114 degrees. So we shouldn't have froze. So we're figuring that out. But altogether, when you think that we touched 140 air handlers and we only had 2 freezes out of everything, it's pretty good. In the past, we would always have, with steam, we'd always have probably about 5 freeze ups in the winter. And one of my staff or one of my managers, supervisors came up, they're like, you know what? This was the best winter we ever had. Because they weren't resetting freeze stats all over the place. They weren't opening up machine room doors just to get air handlers to stay online because we had even temperatures. So, yes, sir.
How much did this project or program cost, and then what was the payback time?
So the steam to hot water project came out to $110 million. Payback is anywhere from $8.5 million to $10 million worth of energy per year. So it's a 10-year project, 10-year payback. For most people that wouldn't do that, but the institution's been there since 1938, the first building. I don't think we're going anywhere. Except, you know, maybe, who knows, but.
Yes. All right, another question from the online attendee. In the future, will you try to keep district steam with its low fuel coefficient for local law 97 and try to improve the heating and cooling systems using district steam instead of converting to gas or electric?
Yes.
And no, right now, we did a quick feasibility study because we're looking at building a new building, and we have to tear the building down, and that's going to kill the steam to actually the Rockefeller Research Lab, which has a whole bunch of glass washers, autoclaves, sterilizers, and cage washers for our vivarium, just to upgrade the infrastructure for electric to change all of this equipment is going to be about $12 million. And that's without buying equipment. That's just to get the electrical infrastructure up to take care of that. So right now we're going to interconnect the steam from the main campus over to Rockefeller and set up and also install a condensate line back so that when we do switch off of Con Ed steam or stay on Con Ed steam, we don't know yet. But when we do get to the next point of electrifying the steam system via an industrial heat pump or some small nuclear reactor, who knows? But until we get to that point, we have to do something. The newest building that we're looking at that is slated to be built starting in 2 years and be built by 2030, that building is going all electric, but we're also going to look at that building, how we can interconnect it to the cooling and heating loads of the buildings next door to it.
Oh, thank you very much, Bob.
One more.
Okay. Yes. How does this stand with the 2030 emission limits?
So thankfully, the city got a little smart and gave us higher numbers for the laboratories. So by combining the 3 buildings into a campus, because now we're sharing chilled water and we're sharing heat, and if I stand alone, the 2 laboratories are fine. The hospital is bad in 2030. If I combine everything, the fines go away until 2035. And then by that time, it's your problem, not mine. I'll be down in Barbados. One last question, and then we have to go.
Out of the 106 million kilowatt hour use, how much is produced on site by the CHP plant?
Nothing yet. I'm sorry. I'm not lying. My friends in Con Ed have yet to give me my permission to operate. We're 2 weeks away. And I've been saying that for the last 6 months. So I'm just waiting for Energy Services to say, you're good to go and we're ready. Thank you.
Thank you all for coming, and thank you so much to our speakers, Caitlin, John, Bob, very informative, fantastic presentations, all of them. Thank you very much. Little housekeeping. If you apply for CEU credits, they come, if you're here, they'll come later in an email. Plus people on virtual land, they got a quiz. They should have gotten a quiz via the chat. Thank you to NYIT for the space. And unlike at Citi Field and at Madison Square Garden, we don't have anyone to clean up under the seats. So please don't leave your rubbish under the seats. Bring it with you, bus yourself. Or if you want seconds, there's more pizza out there. So thank you very much. See you in March.
I know you.